Okay. What we're going to do now is we're diving more into this quantum mechanics idea. We're going to talk about Bohr as we do this. This is Niels Bohr. He has a huge contribution to quantum mechanics and uh, chemistry and physics. There it goes. Okay. So this is all going to start with something called a line spectrum. So how this works is and we talked about this a little bit when we saw the spectrum, right? If you use a pure white light that comes through this slit, the prism gives you every wavelength possible out by separating all the wavelengths. Here, what we're doing is um, they're using hydrogen in the tube, and hydrogen emits light out, goes through the slit, and when it splits off, we're only seeing four particular lines. This is the line spectrum um, as we look at it. Okay. Mhm. Okay, so this is what we know now. Okay. And we're going to go through this and then not come back to this picture, but we're going to get to how Bohr figured this out. Um, Essentially, what's happening is an electron is in a higher level and loses energy to fall down to a lower level. When it's losing the energy out, it emits this energy as light. And because the energy is different for each one of these transitions between the different energy levels, you see different colors because each one is a different energy and a different energy is a different wavelength. Okay, this is where we're headed. I kind of gave us the answer at the beginning. Um, Interestingly, and another thing that was mildly perplexing about this was that different elements had different line spectra. Okay. And so a lot of people worked on this as we're going through it. Um, One of the first people to work with this was a guy by the name of Balmer. I'll write it because I don't know if I said it right. Balmer. Okay. And Balmer developed an equation that explained the visible lines of the hydrogen spectrum. A little bit later on, Rydberg came along, and Rydberg defined an equation that did all of the lines of the hydrogen spectrum, not just the visible ones. And Rydberg has an equation that looks like this. You do not need this. I'm just writing it so we have it. R sub infinity, that's the Rydberg constant, times 1 over n 1 squared minus 1 over n2 squared. Okay. We have to define that n2 is greater than n1 and that these are integers. Okay, this is what the Rydberg equation is telling us. Rydberg constant is really large, 1.098 times 10 to the 7th inverse meters, so we can get through that. Okay, this didn't really explain where the lines were coming from, but they could calculate the wavelength of the line uh, this way. Okay, so, but it still didn't really, where am I at? Oh yeah, Bohr sought to really explain uh, the hydrogen line spectrum, aside from just giving an equation to each thing. Where do these lines coming from, and how do we get them? So if we think about this, let's review what we know already. We started off with a solid sphere. This was Dalton's model. Okay, and then J.J. Thomson and Millikan came around and said, "Oh, wait, there's electrons." So now we have a plum pudding model. Okay. Uh, and then Rutherford came along and did his cold foil experiment and said, well, really, we have a nucleus with a positive charge that where all the mass is, and the electrons are out here, and it's mostly empty space, and we have a nuclear model, or the Rutherford model. Okay. Now we're seeking to explain why. Okay, these electrons at this point are existing kind of randomly out in this cloud of nothingness. Um, and they want to explain why we only get discrete lines in the line spectrum. Okay, fair enough. So they kind of postulated, because we knew about uh, and I'm apparently not super good at drawing circles, uh, the solar system and all this, and they said that, okay, electrons could be orbiting the nucleus. Okay, there's probably a lot more than what I'm drawing, but I'm just gonna draw some in there. Okay, but what classical physics is saying here is that if this is true, and these are orbits, that uh, being near the positive charge, the electron is going to lose energy and crash into the nucleus eventually. And that's not what happens. We have stable orbits around the nucleus, is what they're assuming. And so what they're seeing doesn't jive with what the physics is telling them. Okay. Um, so Bohr and his big idea was that Bohr said, what if the energy of the orbits is quantized? Remember, this word quantized just means only existing at specific levels, right? Puppies, steps, piano keys, all that. Um, and that electrons that are not in an allowed orbit will crash into the nucleus, but electrons that are in the allowed orbits uh, will not. They won't radiate their energy. They won't crash in the nucleus. They will just orbit stably because they're in the allowed quantized orbit of this. Okay, sure, that makes sense. Um, oh yeah, and just for reference here, our secret word for this is duck. You know, quack quack, duck. Um, anyway, so he came up with the Bohr model. Okay, the visible lines in the spectrum. Well, he said all of the lines in the hydrogen spectrum are coming from electrons falling down or relaxing from a high energy level to a low energy level. They're giving off that excess energy as light. And that the visible lines, he called the Balmer series after Balmer, who came up with the equation for visible ones. The visible ones are all going from high energy levels at n equals 2. There's ones that emit more energy. These are going to be out towards the UV. These are going to be out in the infrared because they have less energy coming off of them. Okay, but Bohr said, okay, the energies are coming from this transition. And he calculated stuff and worked through things and came up with that the energy, I'm not entirely, oh, I see what I did. Okay, that the energy of a level is equal to this particular expression. Okay, what he's done here is he's defined that the energy of a free electron is 0. So electrons in atoms have negative energies, which is why we have these negative signs in here. Okay, this is essentially saying that the value of n equals infinity, right? It's infinity levels away from the nucleus. Okay, and it's the most negative at the ground state, and we're defining the ground state here as n equals 1. We're going to use this term a lot, ground state. Okay, ground state is the most stable, right? The lowest energy, right? And this is a negative charge, so the lowest energy situation is going to be closer to the positively charged nucleus. Anything that has an n that's greater than 1, so all of these guys are excited states. Okay, and so the excited states have more energy, and so they're excited. Okay, and so Bohr's theory has come to tell us that energy is absorbed to go up levels, right? So if you're down here at n equals 1 in the ground state, you can take on more energy, go to n equals 2 or n equals 3. But it also says energy is released when electrons fall back down, and they can fall between any energy level that they want to. okay, or radiate, as you want to think about it, okay. Um, and what he had said is that the energy or the change in energy, there we go, the change in energy is equal to the difference between the two levels. Where did you end up versus where did you start? Okay, I have it here too. All right, so ultimately, we have come up with this equation to help us figure it out. Okay, so the change in energy, remember, energy is Planck's constant times the frequency. Okay, um, and if we substitute in Planck's constant and the speed of light, we can solve this for wavelength. Now, the hazard with this equation is that we're solving it for 1 over the wavelength. Let me define the variables here. I have another video where we'll actually work a problem, just so I have that separate so we can just see it. Okay, so this is our wavelength. Okay, h is Planck's constant, which is 6.626 times 10 to the minus 34th joules times seconds. You'll be given that value as you do it. C is the speed of light, which we're going to call 2.998 times 10 to the 8th meters per second. Okay, there we go. The n values here are energy levels. Okay, so these are our integers. Okay, I'll work through an example with this in the next video. Let me know how it's going. I'll see you.